So good morning, everyone. Welcome back. So our first talk this morning is Vincent Stafford from Florida Atlantic University. His talk is a mathematical approach to cost optimization algorithms on quantum computers. Vincent?
Hello, thank you. As he said, I'm Vincent Stafford. I'm a first-year student at the Honors College of Florida Atlantic. And let's skip the party and let's begin. So, quantum computers, you've probably seen them in the news, and usually it's because there's always somebody who's afraid of having their password stolen or their encryption broken by them. And this all comes from exactly one algorithm, back in 1996 actually, Shor's algorithm. And all this said is that quantum computers can factor numbers a lot faster, a super polynomially faster than a classical computer. And before we go on to contextualize what that means, all algorithms we classify into classes of complexity. And the ones you see most are P and NP. P just means we know that we can solve them and verify them in polynomial time. While NP, we only have that guarantee of being able to verify them in polynomial time. And many problems, including factoring, I believe, fall into that latter category. And the optimization problems I will be talking about tend to fall into NP or NP card. So, what's cost optimization? If you've taken Calc 1, you could multiply them. It's just the act of finding the minimums or the maximums of some function, which we like to call C of x. And while it annoys you in Calc 1, it's everywhere. So, I'm sorry. We use them a lot in machine learning, engineering, chemistry, and one use I'm familiar with the most is backpropagation in neural networks. And this is all reliant on a form of gradient descent. So they're everywhere. But like in neural networks, like in machine learning, many of these cost functions are multidimensional. And once you get into physics or chemistry, then they also tend to be complex valued. And these two factors together make them very difficult classically to compute. So, as computer scientists, we are pretty lazy people. We don't like doing what's hard. So I'm gonna throw a dart at the board. I'm gonna see if it hits. And that's not very useful when we're solving math problems. In fact, there's only a minimal chance that we find some sort of minimum when we just randomly set our parameters. Another approach as computer scientists take to solving these optimization problems is we try Bayesian optimization. The problem with that is that it's very complex mathematically, and even if you get a PhD in mathematics or computer science, you're usually going to see Bayesian optimization. So you're got a very limited number of people who know about it. So, and then finally, the best and the most laziest solution is just to build more computers. But it's expensive to have people build your computers, and computer parts, they're pretty expensive. So I'm going to talk about the secret fourth solution that nobody asked about, quantum computers. So let me give you a quick introduction to how quantum computers work. And so if there's one thing we need to talk with, it's that quantum computers, the main difference from them to classical computers is that we use entanglement and superposition to conduct numerous computations at once. And so there are many frameworks we kind of try to build these computers from. The one you see literally all the time now, and one of my research is the Gates model of quantum computation, but one that was a lot more popular about 5 years ago, and is actually a lot of the theoretical basis behind the class of algorithms I'm going to cover. It's called adiabatic computing. And actually this picture here, other than being pretty, this is a chip produced by D-Wave that was an adiabatic quantum computer. I believe it had 2,000 quantum bits at the time. But back to the Gates model, it works like any other logic circuit. The main thing is that we are confined to a very small subset of logical gates that are unitary, and these are represented by unitary matrices, but I'll get into that in a second. And they're very prone to errors. They love to mess stuff up. And so we have an entire class of algorithms and computers called noisy intermediate scale quantum, and the entire goal, our entire goal making these quantum algorithms is to minimize the amount of time we use them. Basically, it sounds a little counterintuitive, but we don't want to have errors destroy our solutions. And so notation, perfectly to have at 9 in the morning, a bunch of city math. And so mathematically, any quantum bit is a state vector that resides in a two-dimensional complex Hilbert space, which I'm sure is very enlightening on its own. But the only thing really to take away from this, and that you should take away from this being new to the field, is that as we add more qubits, the dimensionality of the space they reside in grows exponentially. It's represented by tensoring that two-dimensional complex space n times for n qubits. And so for 4 qubits, it would be a 16-dimensional space, and so on. Any vector inside that complex Hilbert space we can call a state vector, and we use Dirac notation from physics to represent it, so this is ket psi. And then another way to look at it is that states are linear combinations of basis states. And what this means is, think of a quantum bit as like any other quantum system. There's two energy levels. And those are the only ones it can collapse into if it's in some between state. And you may be wondering, why am I pointing at this weird circle so much? And this is what we know as the Bloch sphere. And the Bloch sphere helps us visualize these quantum states. So we have our poles, which are our basis states, 0 and 1. And the closer we are to each pole, the closer the quantum state is to each pole, the more likely it is to collapse that state when we measure it. And then there's also phase, which is going around the surface of the sphere, but that, while it's important, is a little bit more difficult to explain. So I hope you all can excuse me for time there. And then finally, quantum gates are just unitary matrices. And if you haven't heard of unitary matrices, it's just when you have a complex valued matrix, taking the complex norm of it transposed, and then multiplying it to the original matrix gives you the identity one, the identity matrix. And so that sounds counterintuitive, but it's to comply with the similarly named unitarity principle of quantum mechanics. Once again, for the sake of time, I'm not going to get too far into that here. And so let's talk about the actual way we solve combinatorial optimization problems on quantum computers. These algorithms fall under the umbrella of variational quantum algorithms, and we call them that because while we evaluate on the quantum computer, we evaluate the circuit, we actually do the math on the quantum computer. We then take those results and we feed them to a classical optimizer to help us interpret the results, tune our parameters, and prepare us to run it again on the quantum computer. Sort of like the process of machine learning. And so usually there are 2 parameters, which we call beta, which represents our problem, and then gamma, which we call the mixing parameter, which I'll get into towards the end, that we try to optimize. And so, as I said before, we kind of try to represent problems as Hamiltonians. And what Hamiltonians are, in the simplest form, is that they're sort of a function, they are like the functions, I think, that represent wave functions. They represent the wave function of whatever quantum state or whatever quantum system that we're looking at. And so, to do this, and to utilize these algorithms, there's 4 steps. There's 4 things we have to do. First, we encode a reference state. Then we prepare this fun little thing we call an ansatz. We then evaluate and measure our state, and then we tune it on the classical computer. So let's dive into the steps a bit more to get a bit of a better understanding. So our first steps, reference state preparation. This sounds confusing, but it really isn't. We're just encoding some unparameterized state. It's just some subroutine. And so mathematically, we call it U sub r, and it's just the product of any number of unitary matrices. And there are many methods of state preparation. The one that we're going to see the most is called uniform superposition, and it is for n qubits. U sub r is just what we call the Hadamard gate, 10 to n times. And what the Hadamard gate does is if you remember the sphere and the poles, the Hadamard gate, if you're starting from 0, takes it directly to the equator and places the qubits on the equator. So that's what we call a uniform superposition. There's an exactly 50% chance it collapses to 0, 50% chance it collapses to 1. And so we see this a lot in the what we call the quad sum approximate optimization algorithm, which is what I'm going to focus on the most here. Another one is just we call all zeros, and if we're starting at 0, we do nothing. We see them there. They can figure it out themselves. And then finally, if you were a chemist, I'm not a chemist, but if you were a chemist, a lot of times they will use Hardy-Fock state preparation, which is just, in short, it's just trying to approximate the Hamiltonian of whatever chemical system classically, and then working off an estimate on the quantum computer. Whoa, what happened? Oh, there we go. Ansatz preparation. So this is the next step. So we have our reference state, which actually on this picture, and I looked at my time, I'm actually a bit ahead. You see these three pink gates. These are the Hadamard gates. These are placing them on the equator. And now we're talking about the rest of this, the purple stuff. And so at a high level, what this subroutine does is it encodes our parameters onto the quantum computer. And so I'm going to talk about one problem and one application of this, because the way we do this is incredibly specialized to what you're doing. So the max cut problem, I don't know if you all have heard of it, but the short of it is that given a weighted or unweighted graph, we are trying to find a way to divide the edges, or divide the nodes such that the weight or the number of edges between the two different subgraphs is maximized. And so this is classed as an NP-hard problem. It's very difficult to compute classically. And so sometimes this encoding can be as simple as a rotation by the parameter. In this case, what we kind of have going on is if you think of each qubit, we see Q0, Q1, Q2. These are all qubits. You can view, they're kind of representing the nodes of the graphs. And then the control gates sort of represent the edges between them, if I recall correctly. And then we also then do rotations over the x. And specifically, we do Z rotations, which is phase, going around the equator, by our gamma parameter. And then we go around the north to south, you could call it, by our beta parameter. And as I said before, each qubit is a node. And while that sounds complicated and it is complicated, the main point is that we're just trying to get our parameters on the quantum computer. We're trying to sort of build our problem on the quantum computer so that we can then evaluate. So evaluation. Before we evaluate our quantum approximate optimization algorithm, like if we were finishing that circuit for our max cut problem, we need one last set of gates, which is called the mixing Hamiltonian, or the mixing operator. And so we define that as a rotation by our gamma parameter along the x-axis for every qubit. And you may be asking, if we spent all this time to try to derive a solution from our parameters, why would you want to just throw it, like get rid of it? And the reason why is that we're trying to find our way out of local minimums. So if we think of a really simple trivial example of x cubed plus 3x squared, there's a local minimum here at 0. And so if let's say our quantum algorithm started at like x equals 5, it finds its way all the way down here, and it say, oh wow, there's a flat spot here, and it immediately goes up with a similar slope. So like, why would you want to leave that? And so, once again, this is a toy example. With our mixing Hamiltonian, we would sort of throw it out. We'd force it out, and we do that by rotating these qubits. And so what this tries to do, for example, in our toy example here with x cubed, it would just throw it over and then give it to an area of theoretically infinitely low cost. Obviously, the functions are significantly more complicated than that, but that's the idea behind it. And so as we run through the subroutines of this algorithm, because remember what we're doing is we are running this on a quantum computer, where then we're feeding the information to a regular computer to optimize. What we're doing is we're going to start with that second parameter, our gamma parameter, being really high, and so it sort of jumps really frantically between what it thinks to be the solution and what the mixer thinks. And then as we do more subroutines, as the classical computer feeds information back to the quantum computer, and we run through more and more iterations and keep altering our parameters, gradually this gamma parameter decreases to eventually 0, while our beta parameter, which represents the problem Hamiltonian, rises. And so after we do all that silly stuff, we want to measure. And so if you're not familiar in quantum mechanics, if a state is in a superposition, it collapses when measured. The example that we always see is Schrodinger's cat. You don't know if the cat's, yeah? Oh, sorry. We don't know if the cat's dead or alive until you open the box. And in this case, we don't know if the quantum state is going to be 1 or 0 until we measure that quantum bit. And so once we do that, we get a bit string for however many nodes on that graph. And we take that result, and that's what we use to optimize on the classical computer. And so the methods we have to optimize are the same as you'd see in machine learning. The two most common ones is Kobayashi and gradient descent. If you're in Calc 3, I'm sorry. And then before we finish off, let me talk about a real example, because we can talk about theory all day, but what happens if we actually try to run this on a real quantum computer? And so we're working with MaxQuant again. I've already explained the problem, so I will kind of breeze over that point. But we want to recall that for our graph of n nodes, we're going to read out an n-bit string. And this is how we make this plot. We have a decimal version of our bit string solution with them scattered by frequency. I ran one iteration, one subroutine of this, with the beta parameter being approximately 3.15 and the gamma parameter being approximately 0.15. Remember that this is in radians, and so this being really close to pi actually kind of means something. But in this specific subroutine, which I ran 4,096 times, by the way, we get this bit string, which corresponds to this graph. And if you look for more than 2 seconds, that's wrong. That is just incorrect. The correct solution would be this would be orange, this would be purple, and that would be purple. So what happened? Why was this wrong? Well, instead of just interpreting the mode, I guess, of this distribution, we can look, because since these problems are easy to verify, we can look at the correct result. We can look at all of the frequently occurring results, and we see that the correct ones were just inverses of each other, because obviously it does not matter if they are colored the same, which color they are. These two bit strings appear 17 times, which is a lot more than our mean and median, which are both around 3. So that's good. But 17 and 44 are still pretty disparate numbers, especially when in this case the standard deviation is only like 1.5, I think, if I recall correctly when I was reading this. And so the real thing that we can take away from this is that this only represents a single step in our optimization chain, and that we can feed these results back to a classical computer when we're done with this to reinterpret the results, re-alter the parameters, and see if we can get the correct results to appear more frequently. And then the last one, which I didn't put there, is that these computers are very error prone. I said that before, I'm going to say it again. They mess up a lot. And that is our main problem with using them, is that if we're constantly, it's to fight the errors, fighting the decoherence that is inherent in any quantum system, to try to get useful results out of them. So summary, we have the potential to solve NP-hard and NP-complete problems, like our combinatorial optimization in the previous slides, faster than classical computers in some cases. The issue is that the setup is heuristic and is muted at a large enough scale, and that we are trading less accuracy. We can tune the amount of accuracy we want, and so if we tune less accuracy, we compute it faster. And I didn't put the point up here, but it's also really important. We are also at mercy of the complexity of our classical optimizer. So if our classical optimizer is very complex computationally, we're still at mercy to a high level of computational complexity. And so these algorithms find use for our current quantum computers. The issue is that they might be obsoleted once we build large enough quantum computers, once we're able to logically suppress errors. And then finally, minimization of circuit depth only goes so far. As you saw on the previous slide, these quantum computers are still very error prone, and we still can get completely incorrect results out sometimes. And so we have to be careful with how we create these algorithms and how we apply them. And so, references and acknowledgements, and then thank you. Thank you for
Thank you very much. So we might have time for maybe one question, if anyone has one question for Vincent.
So, what is NP hard? I've never heard of that.
Okay, so yeah, so you have P, you have NP, and there's NP complete, which honestly I don't totally remember, and there's NP hard. The thing with NP hard, one of the interesting characteristics is that all NP hard problems can be transformed into each other. So like in NP hard, there's like the traveling salesman problem, there's all these other things, and all the really famous difficult optimization problems are in NP hard. And another thing with them is that I think verifying them isn't as simple as a regular NP problem, if I recall correctly.
And does P equal NP?
That is one of the largest problems in computer science. If you can figure that out, you'll get $1 million. Really?
What's your opinion? What's your opinion?
I don't know. If you look at most papers, they assume P doesn't equal NP.
Does not.
Yeah, that's the assumption that most computer scientists make, but it's really an open field. It could be either way. And a lot of the problems that we have, like here, like the optimization routine being NP hard, if P equals NP, then we could figure out how to make it, then that would be less complex. We could break it down into a less complex algorithm. So really, if you could figure out that P equals NP, you would quite literally change the world.
All right, well, let's give it up for Vincent one more time. So our next speaker is Megan. Megan, are you here? Okay, so